video will be a longer video than usual because I want to walk through some example problems. Now this is going to go very fast. These examples come out of your textbook. They have been pre-worked. The good news is that we're not seeing a lot of lengthy problems with simultaneous equations to be solved like we did in mesh current and node voltage. But there is a little bit of calculus involved, and so I just want to step through these problems. Probably you're going to have to either watch this video more than once or go back through the slides, which will be available on Blackboard. Go back through the slides and try to work through these problems yourself. Don't think that watching me give a brief overview without you doing some practice is really going to cement this in your mind, because it is a little bit different. So first of all, we just want to start out with the very basic formulas. So we have a 5 microfarad capacitor and we're given a voltage. Let me get my full screen going so that I can get a pen to make some annotations. So we're given a voltage, V of t, and what we want to do is calculate the current. So this is a very simple plug into the formula kind of problem. So we just use the formula C dV dt, plugging in 5 microfarads. This is my opportunity to remind you that micro is 10 to the minus 6. And then we plug in the cosine function, so also my opportunity to remind you that the derivative of cosine is negative sine. So plug all of that in and do the calculation, and basically you end up with the solution. So very easy. So let's look at another example. Okay, in this case, we're actually given the capacitor current and we're asked to solve for the voltage. So you may remember that you have two formulas actually that relate current and voltage in a capacitor. One is, in the previous example, we used I is C dV dt. That's because we were given V and we wanted to find I. In this problem, we have the opposite situation. We're given I and we want to determine V, so we have to use this formula. And I'll point out that you always, when you're given the current and need to find the capacitor voltage, you need to know that what the initial condition was on the capacitor. In this problem, that wasn't given, so if it's not given or it can't be calculated, you generally assume that it's 0. Now, on an exam, I would certainly either specify an initial condition or give you a problem such that you could find an initial condition. Okay, so basically then what we're going to do is we're going to take this current, assuming the initial condition is 0, this goes away, and it's just going to be a straightforward integral. So we take 1 over c, that's here, and then we plug in I of t into our integral. We do the integration and evaluate from the limits from 0 to t, and so here's what we end up with for our solution. If you haven't integrated exponential functions with limits for a while, be worth some practice, because in the next chapter we'll be working with exponential functions a lot, so you'll definitely have to get a review there. Okay, here's an example of where we're given a voltage graphically. So this is what we refer to as a piecewise linear function. And the reason we refer to it that way is that this function is divided into regions, okay, where a specific straight line, defines, a specific straight line defines the region. So let's try that again. So I've got the region here that occurs from 0 to 1. It's defined by this line. I've got a region, I'm going to stop drawing my vertical line since I'm so bad at it. I've got a region that goes from 1 to 3. It's defined by this line. Then I've got a region that goes from 3 to 4. It's defined by this line. So linear because we have 3 straight lines. Piecewise because we have to break it up into pieces to write an equation for it. So the first line, the equation for that line is 50 times t. The equation for the second line is 100 minus 50 times t. The equation for the third line is minus 200 plus 50 times t. If you don't remember how to write the equation for a straight line, I would suggest going to Khan Academy and figuring out how to do that. Now, the difference is when you write this function v of t, you have to specify, because it is piecewise linear, you have to specify that this 50t only applies for 0 to 1 second, and this equation only applies for 1 to 3, and this equation only applies from 3 to 4. So if you don't have this stipulation of the time ranges where that function applies, then the way you write your function is going to be incorrect, because these lines are only valid for a certain time range. In Circuits 2, you'll learn a different and more compact way to write these functions using step function formulas. But for now, this is the way we're going to write these piecewise linear functions. So what's going to happen is, because the function is specified over different ranges, we're going to have to break our solution up into different ranges. So remember that I is c dv dt. We were given v, so we're going to have to take the derivative of this function over each time range. So we're going to differentiate this one, and that'll be valid over this time range. We'll differentiate this one, that'll be valid over this time range. So really you can already sort of tell that because the derivative is equal to the slope, we're going to have a positive constant here, we're going to have a negative constant here, we're going to have a positive constant here. So let me show the result. So we take the derivative at each range, we multiply by the capacitance, and we end up with the following result. So we're jumping from plus 10 milliamps to minus 10 milliamps. So our resulting curve looks like this. All right, I do want to make a comment about the mathematical appropriateness of the way this is sketched. Technically, this straight line that's running from plus 10 to minus 10 doesn't exist. So a more mathematically correct way to plot this would be to represent this as a dashed line, because really there's not a line here. Really what happens is you jump from plus 10 down to minus 10 and back up to plus 10. And you know, if you were doing the little mathematician thing, this would be an open circle on this point. Now, do I care about that? No, but mathematicians do, and so you just need to be aware this is an instantaneous jump from plus 10 to minus 10. There's not a real line there. That's drawn for we just say that's drawn as a guide to the eye. It's easier to look at the curve as originally sketched than it is to look at a mathematically appropriate curve with open circles and dashed lines. So and you notice these are less than, they're not less than or equal to. So technically, the way if I had been doing this and I wanted to be mathematically correct, I'd make one of these a less than or equal to, and it could be either one, just so that you don't have the situation where there is no value at 0.1. We'll talk about that a little bit more in Circuits 2 as well, and also a little bit in the chapter on RL and RC circuits. We'll talk about sort of this concept of going right up to the point but not including the point. Okay, so anyway, that's the result, and it is presented both mathematically and graphically. Kind of like problems like this on exams. All right, well, here's a question about energy storage, and it's going to encompass two concepts. It's going to encompass the concept of finding the energy stored on a capacitor, but it's also going to look at what happens when capacitors are sitting under DC conditions. So here's our circuit, We assume it's been sitting here for a very long time, and so it looks like it's DC. It's a DC current source, and so under DC, you might remember that capacitors look like opens. So in order to calculate the voltage on these capacitors in the circuit, we're going to replace them with an open circuit. And if we calculate the voltage across the open circuit, that is the voltage across the capacitor. And you might remember that the energy stored in a capacitor is 1/2 CV squared. So we need to know the value of the capacitance and the value of the voltage. So what we really want to do is we really want to solve circuit B. So the first thing to realize is that if this is open, the current through this 5K resistor is going to be 0, because obviously the big gap here, current has nowhere to flow. So what you really have is a current divider between the 3 kilo ohm resistor and between the series combination of the 2 and the 4. So in this equation right here, we basically are solving for this current, because it's the current that's going to give me a voltage, and getting a voltage is going to tell me what the voltage is across the capacitor. So I do a current divider rule, and I want to calculate this current, so I use the opposite resistor, the 3, over the sum of the 2. In this case, the 2 and the 4 are combined in series, so that's what this 2 plus 4 is. And then that will give you the current right here, this current that he has called I. So now I have this current, which means I can find the voltage across this 2 kilo ohm resistor by taking IR, and I can find the voltage across the 4 kilo ohm resistor also by taking IR. Now, so that means that I'll get 4 volts here and I'll get 8 volts here. Now, notice that this open terminal is actually the voltage across this 2K resistor. Let me erase a couple of lines. Let me erase this one. So you just remember that we've now calculated this current. So if I calculate the voltage across the 2K resistor, then I have the voltage V1, which is the voltage across the capacitor. If I calculate the voltage across the 4K resistor, that's the voltage from here to here. And so the question for you is, why am I saying that's V2? Why is there no voltage drop across the 5 kilo ohm resistor? The reason there's no voltage drop across the 5 kilo ohm resistor under DC circumstances is that this is an open circuit and there's no current through the 5K resistor. So if the current's 0, the voltage is 0, which means that this entire voltage from this node to this node that appears across this 4K resistor will have to appear across this open. So that gives me the voltage across the 2 capacitors respectively, and I plug that into the formula for the energy, and there's my result, 1/2 CV squared. All right, the final example that I want to do on capacitors is I want to do an example of equivalent capacitance. And remember that capacitors combine in the opposite way that resistors combine. So I want to find the equivalent capacitance looking into terminals A, B. The typical approach is to start at the opposite end and simplify toward the terminals. That avoids putting things in parallel or series that may not actually be in parallel or series. For example, this 60 microfarad capacitor is not in series with the 20 microfarad because there's all this other stuff out here. So I want to simplify it from this direction in most of the time. That's a good approach. So the 20 and the 5 are in series, so that means since they're capacitors, they're going to combine as inverses. So I can do my product over sum rule like I had resistors in parallel, and I get 4 microfarads. So I can mark out this part of the circuit and replace that with a single 4 microfarad capacitor. And when you do that, then it becomes obvious that you have 3 capacitors in parallel, the 4, the 6, and the 20. Remember, capacitors in parallel add, so I can just add those together to get a 30 microfarad. So that means that entire, and don't do as I do here. If you're on paper and pen, you need to redraw this whole circuit, because if you start doing this, very hard for me to grade, very hard for you to follow your work. So here's my 30 microfarads right here. It replaced all the rest of this circuit. I'm not redrawing it because very hard to draw with the touchpad. So now the 60 and the 30 would be in series. I use the product over sum formula for capacitance, for capacitors in series, and I end up with 20 microfarad. So very easy. I think you'll find the problems in this chapter, once you get over the conceptual issues, are very simple. All right, so let's switch then and look at some examples with inductors. So this is an inductor, a 0.1 Henry inductor. You're given the current. This is a very simple plug in the formula problem. So V is L d I dt. We have L, we have I. So just plugging in, you're taking the derivative of this current function. It's a product, so you can use the product rule. Taking the product rule and simplifying, you get a very simple expression. Now, if we want to find the energy stored, we have the voltage, or I'm sorry, we have the current given. So we're just going to plug that in for I, and we'll get an equation, and the equation has a T in it. So what this is saying is this inductor is storing energy, and the amount of energy it's storing is a function of time. So if you wanted the energy at a particular time, say you wanted the energy at 3 seconds, you could plug 3 in here, and you'd find that you get an expression for that inductor energy. Okay, this is a similar problem to one we worked before. So in this case, we have a voltage that's given by 3t squared, and that's applicable for t greater than 0. It's equal to 0 for t less than 0. We assume that the initial current is 0 because we're not given one. So we want to find the current in the inductor, and we want to find the energy stored at a particular time. So we first of all basically use our formula where if we're given a voltage, we want to find a current. So we're going to have to use the integral form. Instead of L d I dt, we're going to use I as 1 over L integral of V of t dt plus I at t naught. Now our initial condition, as we said, we were not given an initial condition, so we have no choice but to, and we can't calculate one, so we have no choice but to assume that that's 0. And then our L is 5. We plug in our equation for V, integrate that, and we end up with 2t cubed amps. So the power is V times I, or 60t to the 5th. We can calculate the stored energy by integrating. Now, I wouldn't do that. I would use the fact that the energy is 1/2 Li squared, and I would calculate it that way. You initially had 0 energy stored. At 5 seconds, you would plug in 5 to your formula for current. So that's what I would do, and then you would subtract off 0 energy because that's what was initially stored. Now let's talk about that a little bit. Let's suppose that you had, and for whatever reason their answer looks wrong to me. I have not plugged this into a calculator. Something looks off. Let's put a question mark there. Oh, I see. It's a significant digits issue. So I think they're okay, because notice our units here are kilojoules. I'll be honest, personally, I like seeing things given in scientific notation. So I might say 1.56 times 10 to the 5th joules, but that's kind of a matter of personal preference. Okay, so anyway, I would use the 1/2 Li squared formula at 5 seconds. So what if you wanted to know the energy that was stored between 2 seconds and 0 seconds? Well, you'd find the energy stored at 5 seconds, and then you'd find the energy stored at 2 seconds, and you'd take the difference. Okay, here's a problem similar to the one we worked before, only in this case, we have a capacitor and an inductor, and we want to find the stored energy at t equals 0. This is a DC circuit, so everything is constant. We want to find the stored energy in the inductor and the capacitor. So in order to do that, we need the current through the inductor, and we need the voltage across the capacitor. The capacitor is an open, the inductor is a short under DC conditions. So what that means is no current's going to go through this 4 ohm resistor. So all the current's going to go through a single path. So the current will just be 12 volts divided by 6 ohms, or 2 amps, making the voltage across this 5 ohm resistor 10 volts. Here are nodes here and here. The 10 volt drop occurs between the top and bottom node because the 5 ohm resistor in this path is the only thing that's there. So that must mean I must have a 10 volt drop across this branch as well. The voltage across the 4 ohm resistor is 0 because this is an open, so the entire 10 volts will appear across the capacitor. So there's my there's my DC voltage across the capacitor. The inductor is basically in this loop where we calculated the current to be 2 amps. So the capacitor energy is 1/2 CV squared, giving me 50 joules. The inductor energy is 1/2 Li squared, giving me 4 joules. Okay, in this problem, we're just finding an equivalent inductance. This is a very easy problem. It is just like finding the equivalent resistance. If these were resistors, because inductors combine like resistors do. So the first thing to do is to combine these 3 in series, replacing that with a single inductor, which would have a value of 42. That then places the 42 in parallel with the 7. That combination can be done here, product over sum, giving us 6 henries, meaning everything to the right of this can be replaced with a single 6 Henry inductor, putting 3 of them in series, meaning your equivalent inductance is 18 henries. Let me really strongly recommend again that you do not try to do this calculation by making marks on the existing circuit. I cannot give partial credit for that because that's not the kind of work that I can follow. You would need on an exam with each of these steps to re-sketch the circuit showing the simplified circuit. Some of you will completely ignore this and you will be upset with me when you don't get partial credit. So please, you cannot re-sketch a circuit too many times. In this class, you're getting plenty of time on exams to do that kind of thing. Alright, I wanted to show this one because I think it's super cool, and we're going to do another project with op amps where we use an op amp as an analog computer. So we have our op amp, and so first let's look in the feedback loop, and you notice we don't have a resistor, we have a capacitor. So that means we've constructed an integrator. But notice at the input, you don't have a single input, you have 2 inputs. You have V1 and V2, each of which is connected to a different resistor. And so what you've really built here is you've built a summing integrator, or an integrating summer. So the input here will just be the weighted input of V1 and V2, and then the instead of just simply summing with a feedback resistor and each thing giving you the ratio, we now have V1 integrated with 1 over R1C, where R1 is 3 mega ohms, and V2 integrated with 1 over R2C. So our equation then looks like this. It's got the negative sign because it's still going into the inverting input. You have the first voltage weighted by minus 1 over R1C. You have the second voltage weighted by minus 1 over R2C. And then each of these voltages was given as a different mathematical function. Okay, so what does the output actually give you? It gives you the integral of 10 cosine 2 of t times this 1 over RC factor, and the integral of 0.5t times its 1 over RC factor. So when you simplify that, you end up with the following expression. So what you've actually used is you used an op amp to sum and integrate two different inputs. So this can be done with op amp circuits, and I think it's a very cool thing. It allows you to do some, it allows you to do in circuit form an integral, sum of an integral actually. All right, well that concludes the section where I work some examples on inductors and capacitors. There's a lot here, so as I previously suggested, I think you either need to have this video handy to watch it multiple times, or have the slides handy and go back over those and make sure you understand how to work each problem, so that when you do the homework and or quizzes / tests, you'll have a better idea what you're doing, because you're not going to learn this just by watching a 20-minute video.